which I've now done. So good, or welcome, I should say, everybody, to our weekly call. As you would have heard, we're now being recorded, so do bear that in mind. It's been an interesting week over the last week. You may have seen the announcement from Google that, I'm not sure if it's an official announcement yet, but the suggestion that Android 13 or Tiramisu will add support for Do alongside the sort of native support for Dot. I think due to ship sometime next year. Just so you're aware, I have reached out to the Google team to see if they can join us on a future call to talk some more about that and add a bit more detail to the announcement. But in the meantime, for this week, we've got sort of two topics of conversation. The one that we'll come to in a short while with Vinny will be discussion about the sort of announcement on Friday of Cisco's support for DDR within Umbrella. But before that, our first sort of topic for today, we've been joined by Levi and Dinil from the, I'm not sure which way around to put this, but I think University of Singapore, National University of Singapore, and also Trustwave. I think you both wear both of those hats, but you can explain that yourselves. And this is on the back of a very interesting paper that you published a short while ago that it seemed very relevant to talk about some more here. So without further ado, let me hand over to the two of you. If you need any help with the screen sharing, shout out, but otherwise I'll let you drive and sort of take us through your presentation.
Okay, thanks. So let me try to share the screen. I think I can share the whole one. Maybe. Just a sec. We usually use Teams, so I'm not quite used to sharing the screen with Zoom. But let me try. Still struggling. Sorry. Again. Oh my God.
It should be a case of pressing the green arrow and then selecting the relevant window.
Yeah. The problem is that I actually have a new company laptop, which is a Mac, which I didn't use too much before, and it's a little bit strange. But let's try again.
Something is that has worked.
Okay, so you see my whole screen or only my slideshow?
We can just see the PowerPoint at the moment. Not in presentation mode, but
do you see now my screen?
That's it. Yeah.
Oh, okay, good. Finally, I was a little bit scared about this. Okay, so let me put this away. So then, hi, and welcome everyone, and thanks for having us, Andrew, here. I'm Levi, and I'm here along with Dinil, and we are going to talk about our very recent work that appeared at IEEE Euro SMP like 2 weeks ago, and we kept the same title, which was Privacy of DNS over HTTPS, Requiem for a Dream. And I know that most of us here are very familiar with privacy, DNS, DOH in general. Well, let me have a very quick background that I can share you to let you know how we ended up basically here. So when we start to talk about this domain, we usually try to say something like this, that since the Edward Snowden case and the mass surveillance of the NSA, privacy became of utmost importance. And as one of the main results, basically we see today that more than 90% of the web traffic is using HTTPS. But if you're considering the sensors are still fine. So they are not really care about HTTPS nowadays, because we all know that every website visit is preceded with a bunch of DNS queries. And as long as DNS is plain text, then the sensors are doing fine. They can still redirect you, they can still block you, or even just use the data, what kind of websites you visit, and just monetize it later on. So then the question immediately arises, can we encrypt DNS? And even though we had encryptions for DNS like DNS script and DNS curve for a while, they didn't really penetrate the internet. I don't really know the main reason of that, but maybe because it was not standardized by IETF and they didn't have big companies behind them like Mozilla and Cloudflare. But anyway, the very recent standard, which was standardized by the IETF, was the DNS over TLS. But there was one huge disadvantage of DNS over TLS, which was that it was using a well-defined port 853, which from a censoring point of view, it meant that if you're trying to use a remote DOT resolver, I can just simply block you at the end of my perimeter. And according to another RFC that most of the operating systems and applications implement, which is called the opportunistic user profiles, you will basically silently fall back to plaintext DNS, and it's really silent. So most of the times users don't even know that they fall back to it. So then again came DNS over HTTPS 2 years later. It has been standardized. We also know how it works. But the good thing, or I wouldn't say good because it's a really, it's really a perspective of which side you choose. But one of the most important aspects of DNS over HTTPS is that it's using port 443, the same as web encryption of the web packets. So the problem with this is that they can basically bypass all kind of firewalls. And since it inherently blends into this regular encrypted web traffic, it cannot be filtered and cannot be differentiated and cannot be blocked at all. So basically we had the question then how can we do then censoring after all? So for us, this was kind of like a point of no return, where we saw that all the headlines about DOH end and all the research and the hacks begin. So we digged our head into the different research domains that we found, and basically we identified a couple of ways that people are trying to censor, even if the DNS is encrypted. And one of the things that we found is basically an IP address-based solution, which is quite naive and also not very efficient, but basically there are papers about it, so I wanted to mention this here. So the idea is very simple. Let's build a database of the domains and the IP addresses they're pointing to. But the problem with this, of course, is very simple. The database can be very huge, and to keep it up to date is a very daunting task. And even if we are just considering IPv4, of course, it's already a very daunting task. And on the other hand, nowadays we are anyway in the cloud, so we're virtualizing everything, which means that we are inherently having multiple services running behind the same IP. So just using an IP address-based blocking rule doesn't really work. And from the denial of, from the DNS over HTTPS, sorry, I don't know why do I always say denial of service as a first thing coming to my mind. So from a DNS over HTTPS perspective, we also found this, that if you see, for instance, Container Pi or LibreDNS, those are DNS resolvers that are providing DOH services, but they indeed run their web page and their DOH service behind the same IP address. And there were a more interesting finding we found regarding Cloudflare, that any DOH queries that you basically send to Cloudflare, but specifying a random IP addresses within the Cloudflare domain, those requests will be mysteriously resolved. So you can see here a quick screenshot that I just did actually yesterday. So I just sent a regular DOH request to the Cloudflare DNS resolver, but I picked very different IP addresses that is actually suggested from the older tutorials, and actually it works. So whatever you pick an IP address within the /16 subnet of Cloudflare domain, then all your requests will be resolved. So if you're a censor, you actually have to block the whole subnet, which of course wouldn't be really efficient, because Cloudflare is not just about DOH, right? Cloudflare is also about CDN. So you would end up in blocking a huge amount of the internet. So then the other thing is, which we have to mention, I don't want to talk too much about this, is using the server name indication field in the TLS client hello messages. So that was also kind of a lot of research we found that tries to do this. So basically the server name indication field in the client hello is still plain text, and it can be very talky. So why don't we just parse out this of all the packets, and then we look into the strings that we have to look into. So for instance, Mozilla Cloudflare DNS.com, and then we can use the blocking accordingly. But the problem, of course, with this is that basically nothing stops me using an SNI, which is completely different. So I don't have to have DNS, for instance, in my SNI. I can just use, for instance, penguinrange.com, and it's not really suspicious. No one will think that it's actually a DOH request, right? And on the other hand, we have many other techniques that can actually bypass any SNI-based approach. One of them is like domain fronting. There was a very recent work which was called domain shadowing. Not to mention that an SNI will be basically encrypted using the encrypted client hellos in the future version of TLS, like TLS 1.3, and they will enable penetrate. So at some point, it isn't worth to invest too much into these kind of approaches. And there were a third approach. This is also not very efficient, but we found some people were doing this, so it's good to mention it. There's another tool called JA3 fingerprinting. I don't know whether you heard about this. This is coming from Salesforce engineering. And this method was originally designed for malware detection. And what they do is actually they just took the client hellos and the server hellos of the TLS handshake and take the most important values, concatenate those things into one string, and then they take the hash of it. And that's going to be your fingerprint. But of course, it's very easy to see already that there are a lot of problems with this if you want to use it for blocking purposes, for instance, that the same service with multiple redundant instances behind a load balancer, for instance, can produce different hashes. And this is also true the other way, which means that two different services might have the same JA3 hash. So it's not really an efficient way, but we didn't want to skip this for the record. So then there were other two things that in terms of censoring we can consider is to use the encrypted DNS data itself. So it's not beyond DNS, it's just to use the encrypted DNS data itself, which was already very interesting for us. But basically the first group we found is traffic analysis, which is something like taking the typical website fingerprinting methods and applied on the encrypted DNS data. And the other research we found was basically just scrutinizing how these downgrade attacks can work. So once you block DOH, then what are the performance aspects of downgrading silently back to plaintext DNS, whatever. So these were the very last papers we read. And then we had basically the question that, okay, but then how do we even identify DOH traffic? So most of the research were like, assuming that DOH traffic is already analyzed, and even if in a lab environment, you might be able to do so, we realized that in the wild, it's not that simple. So this is basically our main topic here, and this is what we are trying to solve. So our primary goal in this whole work was to distinguish DOH packets from web packets. And we think that once we can identify the DOH packets, then we can, of course, then block it and force the user to downgrade back to plaintext DNS, or we can use these traffic analysis method mentioned before. Regarding the performance, we really want to achieve an extremely low false positive rate. Why? Because if you're considering blocking the packets, then we want to avoid any noticeable disruption to the web communications. For the classification granularity, we can do this kind of analysis on a packet level versus, the packet level basis and also flow level basis, but we eventually picked the packet level basis because it's more fine granular, and then we can implement kind of like a real-time approach. So every packet we can quickly decide whether it's DOH or web, and then we can make decisions accordingly. And finally, we also had another aim, which was kind of like, if we can achieve our primary goal, then is there any countermeasure, which means that is there any other solution for the users that they can still preserve their privacy that they expected from DNS over HTTPS? So as every research starts with data gathering, so our journey also started with gathering a sufficient amount of data. And for this, what we did is basically we created easy to deploy Docker containers, which are bundled with Firefox and Selenium scripts and Python and Bash, to basically visit the first 20K domains of the Alexa top 1 million domains one by one. And we used all the DOH resolvers we found on it's not like something we can really cite, but it's basically a wiki site of curl where people are collecting the DOH resolvers. So we took the 25 resolvers that we found at that time, including of course the most prominent ones. And then we deploy our containers worldwide. So we were able to deploy some in South America, North America, and also in Asia in our place. So when we have the data, then of course we have the question that what should we look into? So we have a bunch of data what are the important features we can look into. One question is that should we look into 5-tuple? And then of course we were end up like, no, we shouldn't really do that because eventually we would end up in an IP address based solution kind of approach, which we already seen that it's not really sufficient. And then we were like, okay, then should we look into the TLS part? And then because we already seen this fingerprinting method based on the TLS headers, we were like, okay, this is also not a good approach. Then what do we have at all? So what do we have then? So basically, if we only have the encrypted packets, we don't really have too much then the packet length, and maybe we can have some relative features like what is the previous packet's length, what is the inter-arrival time, inter-packet arrival time between the current and the last packet, and maybe we can also have some view about this kind of time lag information for the previous and the one packet before. So these are the features that we could extract from the data set. I know it's very simple, but basically we already found that even if you're using these simple features, they have a really huge overlap. So this was the time when we decided that, oh God, I know that engineers don't really like using machine learning because it's too close to research. But eventually we found that basically machine learning is the only approach we can take because we only have a simple set of features and they are already overlapping. So to capture the correlation between these data, we have to offload this test to some kind of machine instead of trying to figure out on our own. And when it comes to machine learning, we always have to pick what model are we going to use. And people who are very familiar with machine learning know all these models. It's not really important here to remember any of them, but basically we pick random forest. This is something that even people not familiar with machine learning heard about at least once. So we picked random forest not just because it was performing the best in our preliminary analysis, but also random forest is kind of like a model that many networking related research is built on top. So this is the main reason we picked random forest. So, and then I would like to discuss how we evolved our model step by step. So first we use the data set that we gathered for the most prominent resolvers, namely Google, Cloudflare, Quad9, and Cream browsing. And what we did is that we have the data for all of these resolvers by visiting the domains, of course, the first 5,000 domains. And then we label this data set accordingly, which one is DOH packet and which one is web packet. We have kind of this information already because we know the encryption keys, so we can decrypt our files or PCAP captures, and we can see which packet went to Cloudflare or Google and which packet went to somewhere else. So what we did here is that we built the model accordingly, some naive submodels. Each resolver had kind of like a separate model, and we found that basically the closed word setting, which means that we take the data that gathered for Cloudflare and we used it for training and testing. So of course the data set is split into a training part and the testing part. So it doesn't mean that we are testing on the same data, but eventually it's for the same resolver. So this is the closed word setting. It's a very typical thing again in machine learning. So in the closed word setting, our models work quite well, but in the open word setting, they perform very bad. So the open word means that I built a model using the Google data, but then I tested it on data gathered from Cloudflare, Quad9, or Clean browsing. So it's like cross-evaluating the models at some point. So this is the open word setup. But in the open word setup, was very bad. So as a second step, we kind of like, what can we do again? So we try to aggregate a model and also look into some further details. And what we basically did is just merge the data of all these 4 resolvers as a first step. And then we already achieve a quite high closed word F1 score. And then again, there are some other methods that machine learning experts can use to figure out what's happening under the hood. Because normally machine learning is that you give the data and you have a result, but we don't really know how the machine thinks. So there are actually some methods to get some instinct about these working gears. And this is something like called the Shapley values of a model, which basically tries to tell you that what is the most important feature in your data set, which has the biggest impact on the outcome. And we found that the packet length was the most important feature. And then we analyzed the data, and we see that most of the false positives of our model was caused by the fact that the DOH responses are very similar in terms of packet length to the web requests. So then what we did is very simple. We just said, okay, shouldn't we just focus on the requests only? We don't even care about the responses at all because we anyway want to block the request right away. So we cannot really let a whole flow to complete. So we then remove the requests and then analyzed again our performance, and we've seen that in the open-BERT setting we really improved, but there were some resolvers from the huge set of DOH resolvers, those 25 resolvers that we found online, that for our model were performing very bad. For instance, you can see that for DOH.li, OpenDNS, and even Comcast, the results were not that promising. So then we reached our final stage, basically, our final model where we had the original model trained on the 4 most prominent resolvers, and then we merged the 3 worst performing ones. And basically, our final results, considering a very low false positive rate, are these numbers. So in the closed-BERT setting, we have a 0.97 recall value, and in the open-BERT setting, we have 0.9. And the low F1 score here means that basically only 1 out of 10,000 web packets is misclassified. So it's a very efficient way to detect which packet belongs to which class. And then we also analyzed the robustness of our model, which means that we had a model trained in one location and tried to test in other location. And basically, I don't want to go into the details here, but we found that the models are robust enough to deploy in other architectures and other locations. But of course, it's still better for you to do your own data gathering and model building. And then I have just two or three more slides. I'm going to finish it in time, sorry, don't worry. So then we were thinking what are the countermeasures we can have? So can we somehow disguise our model? So the thing that we were looking into is that basically we have 2 fundamental packet characteristics to manipulate. We have the packet length and the time lag. So our idea was that, is there any way to pad these DNS packets to look more like web packets? And there are a couple of things that we considered, from the very basic fixed padding that was also an RFC, but for another purpose, to pad all the requests to the closest multiple of 128 bytes. And we can also use random padding. And basically we can also use a very intricate one, which we proposed that is, we are padding a sequence of DOH packets to a recent sequence of web packets. So what we were trying to do here is that we first tried to analyze which padding method would be the most efficient one. And we only considered the packet length in the beginning. So we built a model using the packet length values only. We didn't really check the time lag, just to figure out what padding techniques to use at the end. So we already found that basically our 5th intricate method, which is padding the sequence of DOH packets to the recent sequence of web packets, is already performing the best in terms of having the lowest F1 score. So what we did is that, okay, we have this padding technique. Let's apply the padding technique on all the features and analyze again everything that we did before. And basically we found that if we are aiming still for a very low FPR values, then our closed-BERT results are basically a coin toss game. So it's 50%. So we really disguise our model. And if you consider the open-BERT part, then basically our performance of the model is 0. So it's a very effective way to still give some privacy for the users. So as a summary, I can say that the first question that we looked into is that, is DOH indeed indistinguishable from web traffic, as all the proposals and headlines saying? And we proved that basically no, we can build a machine learning model on a very simple set of features that can identify which packet belongs to the DOH class and which packet belongs to the web class with a very high accuracy, and also having a very low false positive rate, which is very important, again, when it comes to blocking, because we don't really want to block any web packet. We only want to block DOH packets. And as a countermeasure, we analyzed, is there still some privacy enhancing technologies for the users? And we found that yes, that we studied a wide set of padding techniques. And basically we found one which is able to reduce the accuracy of our model to a coin toss game, or even to a 0% if we're considering open-BERT. Yeah, and that would be it. I hope I could still finish a lot in time. So I just give back the word for the others for the Q&A session.
Fantastic, thank you. Well, I certainly thought it was a very interesting presentation and paper to go with it. And I will encourage people, if you want to ask a question, either use the Zoom feature to raise your virtual hand or post questions in the chat. And I can see a question already posed, which I guess goes back to the how you can defeat your model. And Kurt sort of posed the question about whether the use of DNS-sec would also disrupt the model. I don't know if you considered that or not, or whether that's worthy of sort of an additional consideration.
Okay. Let me go through the questions one by one, so I can also see them from the chat. So honestly, we didn't really consider DNS-sec, but I think that since DNS-sec would introduce some kind of more information in the replies, I don't think it would really has a great impact on our model, because we are basically checking only the requests. So I don't think that DNS-sec has a huge impact on the request, but maybe I'm wrong. So I'm just trying to guess now, because as far as I know, all the things I know about DNS-sec is about having the validation and all the things about the responses, but I don't really know whether there is any difference in the request. So if you can confirm that there is no difference, there's not much difference in the request, then our model would be not really affected by this. But we didn't really check, to be honest.
Yeah, to be fair, if you got it down to sort of zero effectiveness anyway, then you probably didn't need to look further at additional techniques.
Yeah. So then the second comment was, so with padding, the requiem for dream isn't as needed. Yes. So basically, all the promises that were done, that was the thing that we mentioned about requiem for a dream. So basically, DOH in general cannot really give you the promised privacy if a sensor has our model, for instance. But yeah, as we also propose the padding technique, we can make it to be the one that as proposed. Okay, does it work with TLS 1.3? Does it work with DOQ? Okay, what do you mean by does it work with TLS 1.3? I think with TLS 1.3, we mainly think about the encrypted client hellos and all the encrypted SNIs and maybe the zero RTT things. So there are many aspects of TLS 1.3. Can you maybe a little bit more precise about what do you mean by just simply saying TLS 1.3?
Do you want to unmute and maybe just expand on your question?
Yes, when you switch over from TLS 1.2 to 1.3, is the same problem occurs or not?
I think I'm not really familiar with TLS 1.3 in terms of how does it look like on the wire. So according to our features, if TLS 1.3 has a significant impact on the packet length and also on the time lag, then yes, I mean, it would have an impact on our accuracy. But basically, we don't really care about what the payload is. So if TLS 1.3 encrypts everything, we don't care. We only have to do is to just gather the data with TLS 1.3, and we can build our own model again. But of course, I don't know what the accuracy will be having different kind of TLS versions in the packet trace. But eventually, since we don't care too much about the payload itself, it shouldn't be a big impact from that side.
Okay, thank you.
Does it work with DOQ? That's something we also thought, but eventually we found that DNS over QUIC has the same limitations as DNS over TLS. So it is using a well-defined port, which can be easily blocked by a firewall. So that's the reason that we didn't consider DNS over QUIC. But basically the same approach would work. But anyway, we have this simple way to just block it by using that well-defined port. Okay, true triggering request easier. Yes, thanks for confirming. So mixed DNS. Okay, I don't know whether this is a question. So let me quickly go to the other one because I don't want to run out of the time. So it seems to be optimized. So someone is asking, your model seems to be optimized for speed of detection using per packet analysis. Am I understand that correctly? Yes, you are. We really want to do our decision-making on a packet level basis. So once we see a request packet, we want to decide whether it belongs to DOH or web right away. So we're not doing it on a flow level basis. We don't wait for a full flow to be completed because that's already too late to block it. If so, was there any further work on flow-based identification? We didn't do any further work on flow-based identification for two reasons. One of the main reasons is that we already found that our packet-based approach works quite well. And if we are considering sensors, then we should really stick to packet level based work. And there was another work, it was also cited in our paper, which considered actually a flow-based identification. The problem, I mean, not the problem, but the main difference with flow-based identification is that since it's a full flow, you have much more data and much more features to consider. So it would be a little bit different than our model. So of course, if you have more data to consider, then you can build a completely different machine learning model at some point at the end. That seems to be much more promising DOH classification than given the larger packet sample set. Yeah, that's true. Another thing I wanted to mention about flow-based identification is that I don't know whether any of you have checked Wireshark when you're using Firefox and DOH, for instance. So basically, when you fire up your Firefox, it establishes a connection to Cloudflare DNS, for instance, by default. And until you close it, the flow doesn't really end. So it's also something that you should consider when you talk about flow-based identification, that if you want flow-based identification for DOH resolvers, then eventually you have to wait a huge amount of time to let that flow to be completed because Firefox won't really complete it until you close the browser. Okay, the next question. Sorry, do we have time to go through all the questions because they are like,
yeah,
like a storm.
You got two more questions, I think. So I put one in the queue, and then Vinny has, and we'll cut it after that. If that's
okay. Okay. So then Alison Mankin asked, could the model identify DNS requests in a DOH stream because of their timing, because they are honoring TTLs? Could the model timing is a feature, so maybe this is discussed. I mean, sorry, I don't really get what this question is pointing to, but if you
understand, we probably have a bit of a time signature, especially if you were to, put some, because when TTLs expire, the query goes out again. So they may be different from web traffic because they have some repetitive, some of the queries may repeat because of that. So that might allow you to identify DNS queries based on timing. You mentioned that timing might distinguish DNS queries a little bit.
Yeah, we used it as a feature, but do you say that many DOH queries basically can have their TTL values expire before they reach the
No, I was just thinking that you might time. So I didn't see you talk about it in this, but I'll go read the paper. I assume you talked about how time values were one of your identifiers. Padding doesn't help you with timing, right?
Yeah, but basically we can. So we cannot make the time shorter, but we can introduce some extra delays. So we can at least, we can say that we can pad timing at some point.
Okay,
maybe
thanks.
I can just add, so yeah, the timing we are referring to is the time between the packets, and the TTL part, I think, yeah, that's interesting because, the TTLs expire and you might see some more queries, but I guess that would require some study to figure out whether we can do that. Also, because it's encrypted from a network adversaries perspective, you don't see the TTL, you don't know which domains are being queried. So I think it's a harder work if you want to look into that. Yeah.
Thanks.
Dinil, maybe then you can take over from here for the last two questions.
What is the, did you consider the compute cost of the methods to defeat the model? If so, how expensive was it to restore privacy? We didn't really look into that, but it shouldn't be expensive because the final, the best padding technique we use just stores a window of feature values for the web packets. So in terms of computation cost, it shouldn't be expensive, but there is a storage cost if you want to do it at a router, because you're going to do this for every flow. So you need to store the timing, the feature information for a sequence of web packets, and then use it to fake on the DOH packet. So I would think the cost is more on the storage, on the buffer, rather than the compute. Right. Okay.
We have one more last question from Vinny.
Have you evaluated ODOH, and does it differ at all when used with mass proxy? No, ODOH, I guess, is the oblivious DOH, right? No, actually, we haven't looked into it. Not sure how it will differ in terms of on the wire, right, and on data. I'm not sure about that. Yeah. So we haven't. We haven't looked into that. Yeah, it might be interesting to see where it is. Yeah. I suppose some of these like Cloudflare supports ODOH.
Well, I guess it's always good to finish this sort of presentation with further research needed. That's always, I think that's traditional, isn't it, with most research papers? So
it's always the first scratching the surface, right? And then we always have more things to explore. Yeah, right.
Yeah. Now, I think we should cut there, just conscious of the time, but there are some more questions in the chat. So I'll share those with you perhaps offline after the call. And if there's an opportunity to perhaps respond on those offline, that would be fantastic. But I guess the volume and variety of questions, I think, highlights that this is sort of, I think, proven very interesting, and you've captured people's attention. So which is always a good thing for this sort of paper. So I think I'd like to say sort of thank you to you both for taking the time to present to us, particularly at such an antisocial time of day for you. That's much appreciated. And anyone that hasn't done so, I'll share a link after the call again to the paper, so you can also read that. It's well worth reading.
Sure.
But so Levi and Dinil, thank you for joining us. You're welcome to stay on for the rest of the call, but if you want to disappear and go to sleep, that's perfectly understandable as well. But thank you both very much for an interesting presentation.
Yeah, thanks. And I will send you the slide deck in PDF to send with the. Okay.
Yeah, fantastic. Thank you. Right. Well, and with that in mind, thank you both. We now will change tack, so we'll move from sort of research into sort of future improvements that could be made maybe to the whole DOH protocol, and shift to the actual running code part of what the IETF often talks about, and the announcement on Friday that Cisco, within the umbrella portfolio, is now supporting DDR. I think I'm right in saying the first product to ship with DDR support. So Vinny is going to talk to that, and I'm going to share my screen. I assume that'd be easier for me to drive, Vinny.
Yeah, that'd be great. Thank you.
So hopefully this will work. So I believe you can see the slides hopefully on all your screens. Is that sufficiently clear, or should I enlarge the screen?
I can see.
Fantastic. Okay, in that case, Vinny, over to you.
Sure. So we announced on Friday that Cisco has, on our production DOH servers, enabled DDR. You want to go to the next slide. So this is a quick overview of what it is, discovery of designated resolvers. We were not involved in the IETF creation of the protocol, but we wanted to embrace it because we think it's very useful. It essentially allows the discovery of DOH resolvers from the network. It bootstraps from classic DNS to DOH with no infrastructure changes needed, so you don't have to swap out any of your equipment in the network. And it provides for secure bootstrapping with PKI-based proof of ownership. And that's a link there to the spec for those not familiar. Next slide, please. So why did we decide to support DDR? So for us, the seamlessness of upgrade from legacy DNS was important. It's obviously provides a path to a more secure DNS protocol. And the network still acts as a policy enforcement point in this solution. And then, as noted earlier, no infrastructure changes are needed, so customers don't have to do a heavy lift in order to take advantage of this. Next slide. So the use cases and drivers for us to decide to do this, probably the biggest one is that enterprises prefer network ecosystems over device management in order to do enforcement. So it's much easier for them to provision something in one place versus having to manage every single device in their network. Customers still want DNS content filtering. That's a very big ask. So despite maybe the desires not to use DNS for that purpose, it happens to be a very important thing for our customers. Yes, Wi-Fi networks are very popular, and that's a case where you don't have any device management capability, but you still want to apply your enterprise policies to people who join your network. And so this ecosystem provides a way to do that. And then, of course, BYOD and unmanaged devices, which we already covered. In addition, just to give an example, there are customers of ours who actually will secure their own devices that they have on display in their stores using network-based DNS content filtering, as opposed to having to manage all of those devices that they have on their show floor. So it's much easier for them to just do it in the network than to have to manage each one of their own devices. So that's a perfect example. Next slide. So here's a couple links for more information. So we have an open interop where anyone who wants to participate and try out the protocol, they can do that by just going to any one of our production DO resolvers. And as stated earlier, there's a quick link to the DDR protocol spec for those not familiar with it. So the next tasks are we have to get an official IANA assignment. Right now, it's just in trial form. So once that official number is assigned, we'll change our server to support that. And then the other item that we want to look at next is identity in DO, because again, for us, we do need the ability in the enterprise use cases to be actually able to identify users and devices for policy-based enforcement. So that's hopefully something we can work on next in terms of a DO ecosystem. And that's it. Thank you very much. Any questions?
Thank you, Vinny. Again, anyone's got any questions, either put them in the chat or raise your virtual hand. And I can see there are some comments and questions already in the chat, Vinny. So Chris Box is wondering which client you used to test this.
I can't comment on any of the clients that we interoperated with, just because that was under NDA. So I suggest you reach out to those vendors for comment on that.
Fair enough. There are some well-known client vendors out there, so I'm sure people will do that if they're interested.
I presume there were no show-stopping issues with those interrupts then so far?
No, they've gone fantastically well.
Cool. Good to hear.
one of our esteemed co-chairs of the ADD group wanted to emphasize that it's the draft spec for DDR. So duly noted.
Both of the co-chairs would like to emphasize that, please.
I didn't want to put
Yes.
it in both your mouths unilaterally, but in that case, both co-chairs wanted to emphasize it was a draft spec. Thank you, Dave and Glenn. John has said that Quad9 is using a key of 65380 for our DDR implementation. What's the current key that Cisco is using? If you're able to comment on that, Vinny.
Yes, so ours is 65432, which is easy to remember, I guess, but that was the point I was making about we need an official number assigned. And when that happens, obviously all the vendors who are going to support DDR would converge to that number. But right now we're 65432.
Yeah, I guess unique numbers required so you don't clash in your dance moves in the DDR. Pat has asked me whether I can share both presentations, and if that's okay with Vinny, I'll be happy to share.
Yeah, absolutely. And it has a link so that folks who want to get the IP addresses to try out DDR with their client software can do it.
Brilliant, thank you. And John Todd has said also what IP address can be used to test a query for resolver.arpa results.
Yeah, so
I'll read the paper. He just answered that. Perfect timing.
Yes, so we have both IPv6 and IPv4 support, and there's several addresses because we have multiple DOE resolvers. So you can try them all out. Let us know your outcome.
I do remember that in the blog post they mentioned it, Vinny. It did list a variety, as I recall.
Yes, and there's also an email, ddr@cisco.com, that you can send any questions to if you have any.
Fantastic. Right, that's all the questions in the chat. So does anyone want to actually ask any questions? If you can, use Zoom, raise your hand, and you can jump in and ask if you do.
Hey, Glenn here. Let me jump in. Sorry, I don't want to hunt the raise hand button on this particular interface. Hey, Vinny, really cool. Hey, would it be possible for you to also drop a note to the Encrypted DNS Deployment Initiative mailing list? There's a lot of people there that are following sort of developments here, and I think they'd be really happy to hear what you made available here.
Would you mind just shooting me an email with that email address in it?
I'm sure we can get that over to you.
That'd be great. Thank you. And I will send that information out.
And I'll share this a link to recording this call plus the slides to the Eddie list as well. So you haven't got to repeat anything you've already covered, Vinny.
Excellent.
Okay. Anyone else got any questions or comments on the Cisco announcement? Silence is probably not. Hopefully it's the first of a whole slew of similar announcements as people get their code moving. So a good timing just in advance of IETF 112 as well, Vinny.
Yes, thank you.
Right, okay. Assuming there are no more questions then, thank you for that update. That's much appreciated. That brings us then on to any other business. So I'll briefly just say what I think I said at the start, which is sort of hot on the heels of Cisco's announcement. I saw Android 13, Android Tiramisu, will apparently have support for DOE built in when it ships next year, and I'm hoping that having dropped a line separately to the Google team, that one of our sort of soon, or one of our fairly imminent calls, someone from the Android team will join us to talk some about that, because I'm sure that will prompt some questions as well. But I guess that looks like there's going to be a lot more traffic going on to DO resolvers over the coming months, as well, sort of with Umbrella, with Android, etc. So it's going to sort of bump up the traffic volumes quite considerably, I'm sure. I didn't have anything else this week that I've spotted, but does anyone else want to come in with anything else you want to highlight whilst we're on the call? If you do, either put it in the chat or sort of raise your hand or just unmute. As always, I'll give you a minute or two just to do that. I'll take silence as probably not this week. In which case, thanks again to Levi and Dinil for your presentation, and indeed to Vinny for yours. Lots happening this week. Have a fantastic week, everyone, and we'll reconvene same time next week. So have a brilliant week.